This video is a video about taking another look at the reduced row echelon form. So before we talked about the column space of a matrix, and the main theme was if I have a matrix A and I look at the reduced row echelon form of A, that's a different matrix. But the columns of A and the columns of the reduced row echelon form, let's just call that matrix R. The columns of A and the columns of R are related. They're not the same, obviously, and the spans are not the same in general either, but the columns of A satisfy the same dependence relations among each other as the columns of R. So let's just look at an example. Let's say that A is this matrix 1, 2, 4, and the second column is 3, 5, 0, and the last column is 2, 3, negative 4. Okay. So I see that I have these three columns, right? Let's just call this V1, V2, and V3. And let's think about the row echelon, the reduced row echelon form of this. Let's call that R. So one thing I notice about V1, V2, and V3, V1 and V2 are linearly independent, and V3, so V1 and V2 are linearly independent, and V3 is actually V2 minus V1. So the reduced row echelon form, let's call these columns W1, W2, and W3. Those are going to be true of the reduced row echelon form. So W1 and W2 are also going to be linearly independent, and W3 is going to be W2 minus W1. Well, when you think about what the first column is, can you see what the first column, I mean, if you just imagine doing some of the steps, what will be the first column of R, the reduced row echelon form? Okay. It will be 1, 0, 0, because you have you don't have a 0 in the first, the first column of A isn't just all zeros, so you have a non-zero number, and so the first column is going to be 1 with a bunch of zeros. Now what about the second column? The second column is going to be 0, 1, 0. Okay, because it can't be 0, 0, 0, because V2, right, if it was 0, 0, 0, then W2 would be 0, W1. That would mean that V2 is 0, V1, but that's not true. Right? So W2 has to be 0, 1, 0. It can't be 0, 0, 1 because then you'd have a pivot in the third row, but it needs to be in the second row. Okay, and what's W3? Well, W3 is W2 minus W1, so that's going to be negative 1, 1, 0. So you see, we now have another way of looking at the reduced row echelon form. We see that basically whenever you have linearly independent columns in A, those will give you the pivot columns in the reduced row echelon form. And then so here are your pivot columns, right? And any non-pivot column, so this 1, 0, 0 corresponds to this being linearly independent, and the 0, 1, 0 being linearly independent. And any column that's linearly dependent, or any non-pivot column, is going to be a linear combination of the previous pivot columns, and in the same way as this non-pivot column is a linear combination of the other columns. So let's just take a look at another example. Let's say that you had, so that was the first example. Let's just make up a matrix A. So let's say that A is, oh, I don't know, one, like 0 to 1. And then the second column is 3 times that, so 0, 6, 3. And then the third column is 0, 0, 0. And then the fourth column is 1, 2, 5. Sure. What will be the reduced row echelon form of this? Okay, so you see the first column, right? That's not all zeros. So I know that my first column of my reduced row echelon form is going to be 1, 0, 0. Now the second column of A is 3 times, so here's V1, so this, here's V2, V3, V4. Okay. V2 is 3V1. So here's W1. So W2 needs to also be 3W1. So I'm going to have a 3, 0, 0. What about W3? Well, let's look at V3. V3 is 0, V1, right? So W3 must also be 0, W1, and so I get 0, 0, 0. Finally, V4 is independent of V1, V2, and V3. It's not a linear combination of V1, V2, and V3, because any linear combination of V1, V2, and V3 has to have 0 as the first component, and V4 doesn't. So V4 is independent of V1, V2, and V3, and similarly that must be true of W4. So I'm going to have a pivot column. And okay, I only have 2 choices. It's 0, 1, 0 or 0, 0, 1. And since my matrix needs to be an echelon form, I need to have a 0, 1, 0. So that's going to be the reduced row echelon form of the matrix A. Right? So notice when you look at the pivot columns, you start off with this 1, 0, 0. I mean, you would have a 0, 0, 0 if the first column of A was 0, 0, 0, right? But that basically never happens. I mean, in theory it could happen, but okay. But we don't have that. So your first column is going to be 1, 0, 0. Then the next one, so that's going to correspond to here. Then if the next one is a linear combination of the previous one, this second column is going to be the same linear combination corresponding to the other column, right? And it's the same way, you just keep going. So 0, 0, 0 is a linear combination of V1. It's a multiple of V1. And so you make your W2 and W3 multiples of W1. And as soon as you reach one that's not a multiple of the first column, right? So 1, 2, 5 is not a multiple of the first column. Then you have your second pivot column. And you keep doing that until you get to the end. So that hopefully gives you a better idea of how reduced row echelon form works. Because, when you first learn about reduced row echelon form, it's just, okay, when you do all these row operations and you kind of just do the process, and then this is what you get at the end. And you can use it to solve, systems of equations. But here we get a better idea of what the reduced row echelon form is telling you. If you're given the reduced row echelon form, you can actually say a lot about the original matrix. You can say which columns are going to have linearly independent columns, and then you're going to be able to say how the non-pivot columns are related to the pivot columns. So for instance, let's say that your reduced row echelon form was 1, 0, 0, 5, 0, 0, 0, 1, 0. Well, you don't know what your original matrix A is, because A could be, lots of different things. But you know that your A your column 2 of A has to be 5 times the first column of A. And you know that column 3 of A is not a linear combination of column 1 of A and column 2 of A. Right? So that's what you can say about the original matrix A given the reduced row echelon form. And maybe I should just emphasize why, again, why is it true that if column 1, if column 2 of R is 5 times column 1 of R, so we know that column 2 of R is 5 times column 1 of R, why is it true that column 2 of A must be 5 times column 1 of A? Well, if column 2 of R is 5 times column 1 of R, so let's just call this W2 and W1, well, that's the same as 5 times W1 minus W2 is the 0 vector. Which means that, 5, negative 1, 0 is a solution to Rx equals 0. And since the solutions to Rx equals 0 is the same as the solutions to Ax equals 0, we get that this is a solution to Ax equals 0. And since that's a solution to Ax equals 0, that tells you that 5 times the first column of A minus the second column of A is the 0 vector, and then that's the same as saying that V2 is 5V1. So that basically gives you an idea of why the relations among the columns persist when you do reduced row echelon form. Okay, thanks.